going to talk about some of the more important and advanced aspects of using MPI, particularly for performance. So I just want to make sure, how many of you, I want to make sure all of you raise your hand. Have you all done sort of basic MPI programs? Right, everybody, yes, okay. So I was happy also to hear Pete talk about abstract machine models, because that's one of the things that I will be coming back to as I talk about what's going on in your MPI programs and the importance of having an accurate, if still abstract, model of what's going on. So what we wanted to start with this morning is a fairly simple example that can illustrate some of the performance hazards, performance problems that you can run into. And this is going to be a little section on the costs of synchronization. So when we do parallel computing and we write code to move data, one of the things that we're doing, of course, is moving the data. That's the easy part. The hard part for the system, for the underlying hardware, is understanding when all the data has been moved, when things have been synchronized. It's very easy to forget that, but that's a big part of the sort of overall challenges, particularly in making something scalable. Okay, so even with fairly simple operations, you can get some surprising performance artifacts. And I'm going to give an example for a common grid exchange that came from a piece of real code probably about, now maybe 20 years ago. So MPI is actually quite old. It's now old enough to vote and drink. So I think it was old enough to vote at 18. It's now old enough to drink at 21. Okay, so one of the things to note in here is that when you write code, you are going to add requirements on the order in which the code executes. And all of those requirements can impact performance. You'll see some of those when you talk about vectorization and multi-threading. We'll see them here with MPI. Okay, so here's a simple example. The idea here is that we've got some mesh, and I've broken it up into 12 pieces. So this is like the local piece of the mesh. The whole mesh would be one chunk of gluing all these together. And in the typical halo exchange that you use for PD simulations, I have to send my edge data to the adjacent processes so that when it applies a stencil, and I'll go through these if they're unfamiliar to you when we talk about the example code. But it's going to need, computation over here is going to need a little bit of data from these adjacent processes. So I need to send that. And the easiest way to do that is, well, I'm going to send the edges to the neighboring processes and then receive. So what's wrong with this code? Anything wrong with this code? It might block. It might. So it's formally incorrect because the first send, or one of these sends, might not complete until the receive is posted, until there's a place for the data to arrive. The system might buffer it, so it might work. It might work for some sizes and not others. So you've got that problem. Now, there is, in fact, a much worse problem. I say this is a worse problem because the code might run, but it might run poorly. And an example of that is something like this, where first, I only send to the neighbor below me, and then I receive from the neighbor above me, and then I do that for the 4 sides. That code, in fact, will work. If I can go back to this case. In this case, I don't have periodic boundaries, so I'm not sending, the top process is not sending to this process. So, for example, if I'm sending down, this process is going to do it. It's not going to do a receive, so it's immediately going to do a send. The other processes, they have to do a receive, then they do their send. What happens is you get something like this, where there's a process which doesn't have anybody to send to, so it does its receive. That matches the send from the previous process, which can then do its receive, which matches the send from the previous process, can do its receive, blah, 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 blah. And so this code does not deadlock, but it doesn't parallelize either. It serializes each of the communications. And so what you manage to do is get one of the worst things that can happen to you, which is that the code works, but it performs very poorly. And if you're not being careful and looking at the performance that you expect from the communication, you may just think, oh, this is slow, or I've got some other sort of scaling problem. Okay. So there was a group that was building a computational fluid dynamics code. They had discovered this. They'd read a little more about MPI. At this point, it was only MPI 1. And they discovered the Irecv. And as I think we mentioned last night, these non-blocking operations are not, in fact, they're not primarily for overlapping communication and computation. They're, in fact, for writing correct code so that you don't have to order the sends and receives. Now, a drawback of these non-blocking operations is they are a little more complicated to deal with. In fact, there was a very nice article by one of the grand old men of computing, and it was at that time the grand old men, I'm afraid, of computing, about what was awful about MPI. And one of the things that he found really awful were these non-blocking operations, because you have this space between initiating the non-blocking operation and the completion where the programmer is expected to behave themselves. They're expected to not just work with the buffer, change it. There are all sorts of hazards there. In addition, there's some performance costs to having these non-blocking operations. So what this group did, having discovered first that they couldn't do just sends and receives, and one of the reasons they did just sends and receives to begin with, was that some implementations of message passing prior to MPI provided large amounts of buffering. So the sends would work because the data would be copied out of the user's buffer into a system buffer. The send could return. That data could be eventually sent to where it needed to be received. The problem with that is that you had this extra data copy, sucks up performance. People learned that while that made it maybe a little easier for users to program, the cost and performance wasn't worth it. So then they went to this code. You post all the receives, then you do the sends. And then you wait on the receives and you're done. Okay, so this has a lot of nice features. In some sense, it's as simple a piece of code as you can get to that will provide that parallelism in the communication. So we post all the Irecvs, then the sends can go as soon as they get started, and then we just wait for the receives to complete. But what they discovered, and this was great because they did something that even today many people don't do, is they paid attention to the cost of the communication, and they had some sense of what they expected, and they were not getting what they expected. So they asked, well, what's going on? Why isn't this performing well? What's wrong with our code? And that was, of course, also the right question. They didn't assume that the MPI implementation was limited or inferior. They assumed it was their code. That was actually quite generous of them because it was very early. And even today, there's a lot of things that are very difficult to code, to optimize, even for MPI. But that was the right way to start. And so we looked at this and said, just something interesting going on here. So what I'm going to do is I'm going to show an execution trace, thinking of a sort of abstract machine model. And this is the way I'm going to define my abstract machine model. So I'm going to assume that I can send from one process to several other processes. I'm going to assume that the sends block. So there's, say, inadequate buffering. So a send can't complete until the message has been sent on its way reliably. And I'm going to assume that the sends control the timing. There could be other things that control the timing. But I'm just going to assume that if I can push the data out, it gets received at the other end. The receives don't interfere with the sends, except for the fact that I have to be able to receive the data. So if I do that, then that exchange should be done in 4 steps. Right? So if we go back to this code, the number of neighbors in this case is 4. So I post my receives. I assume these don't take any time. I do the sends. So I've got 4 steps. I've got 4 sends. Assume my sort of unit of time is 1 bit of communication of this edge. Bing, 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 bing. I'm done. Okay? But now let's see what actually happens. Okay, and I'm going to assume that the edges are all ordered the same way, that all the processes first try to send down. Okay, so these processes start sending down, these processes start sending down. But the processes on the bottom don't have a down neighbor. So they go through the loop and say the next direction is right. So this process starts sending right, this process starts sending right. This one doesn't even have a right neighbor, but it has a top neighbor, so it sends up. Now, the problem here is that I've got data coming in from 2 processes to this guy. And my abstract model is that it can only absorb a certain amount of data per unit time. And I'm also going to assume that they interleave in the sense that the send operation is broken up into a bunch of little packets. And those packets arrive. And I assume sort of fairness here that this process takes packets from this process and this process in roughly equal numbers, which means it only gets about half of the message from this one and half of the message from this one in that unit of time. Another way to think about it is in a unit time, each process can absorb in bytes. These processes are receiving in bytes. This one is being sent to in. It only receives in, so it receives half of these 2. So what I've done here is I've drawn these with dashed lines to indicate that only half of the data has been delivered. And that happens also for this process and for this process because of this up. Okay. So that's the first unit of time. Now, in our very simple model, it'd be 4 units of time to do the deliveries. Okay, so here's the next step. Well, this process had sent down, it then sends right. That's all nice and easy. This process sent down, now it sends right. These processes have not completed their send. The sends are blocking. So in the second unit of time, it's also sending about half the data. Same thing here, same thing here. Up here, this process had a down neighbor, but no right, no top. So it starts sending left. This process is a right neighbor, but again, we've got 2 in coming into this process. And so only about half of the data from each of the senders can arrive in that step. Just sort of continue this in the next step. Well, after 2 steps, these processes had completed delivering data to this process. So this one can now start sending to its right neighbor. This process that it had no down, no left had sent up. That took 2 steps. It can then send right. So on and so forth. Up here, we get to a point where, let's see, this process is sent down, then right, then up. Now we have 3 processes sending into that poor guy up there in the middle. So on average, they're only going to be able to get about 1/3 of the bandwidth into the node to each of them. So I've changed these into dots. Right? So This actually should be sort of dots for what's left over. Okay, that's the third step. Now, if everything worked as you'd sort of think in terms of each step delivering to that neighbor, at the end of the fourth step, we would have been done. Okay? So what's happening here is, again, these processes are sending to the same destination, so they can't send as fast as they'd like because they have to share the path into these processes. And so, for example, this process here is still sending up. Now, if everything happened really nicely, in the fourth step, everybody would be sending, I think, right is the last one. So down, left, up, or down, right, up, left. So everybody should be sending left, but that's not what's happening. Right. So at the end of the fourth step, we're not done yet. There's a fifth step where these processes continue to deliver data that they have been unable to deliver because they couldn't get the data into the destination fast enough. And in fact, there's a sixth step where these two interior processes, the only ones with 4 neighbors, finally complete by sending data to the left. So this took 50% longer than you would have expected. Now, this is abstract machine model. There's a lot of simplifications here. You won't see exactly this sort of behavior in a real machine. When we looked at this, this was on an IBM SP. It was actually the SP before it was the SP1. And what you see here is this blue here is the send. And in this model, everybody's sending exactly the same amount of data. So the send should take the same amount of time. But what you see, the length of these bars, there are ones that are about this long, there are ones that are about twice as long, and there's a couple that are even a little longer. And then these are also the weights on the receives. If we do a histogram, okay, so what you see here is this peak here. These are the sends that ran about as fast as you would expect. In other words, they weren't contending with other processes trying to deliver to the same process, and that's at about 3 point something or other. At about 6 point something, there's another kind of little hump, and there's another one a little bit out here. These are the ones where there were 2 processes sending in, and this is the one where for a bit of the time, 3 processes are sending to the same destination. Okay. So why did this happen? Well, we told it to do this. By using sends, we imposed an order on the delivery of data. We said that it is important to us that the edges be delivered in a particular order. Actually, that they be sent in a particular order. And in fact, of course, we're doing a halo exchange. We don't care what order the data arrives in. We just want it to be there. But when you put in a send, you say not just move this data. You say finish, at least getting the data out of my local buffer. And realistically, in most systems, the data is going to be delivered before the send returns, right? Because you have that data, you start sending it. What happens if there's a hardware error and some data is lost? The system will do retransmissions for you. You don't have to worry about that. But the system has to be able to get to that data. So typically, the send won't return until it knows that it is safe. That's in order to complete that data. It knows that the data has, in fact, been delivered to the destination, and it won't ever need to look at it again. And so you have enforced a particular order. Anytime you enforce one of these orders, you potentially slow down your code. And it doesn't matter whether it's MPI or vectorization or multi-threading in the code, anytime you add synchronization that's not required by the semantics of your algorithm, you can potentially slow down the code. So what's the fix for this? Yes?
For the first step you mentioned, there are few processes which are receiving like from more than one.
Yes.
So basically they are taking twice as much time as if they would take, if they're receiving just from one, because
Right.
you're getting half the bandwidth. So is each step like taking twice as much time as would it would taken just with the one neighbor?
So let's go back and look at this. So some of the steps, some of the communications take twice as long. So in this simple model, the communication, the send to my down neighbor takes twice as long as I would have expected for this process. For this process, it doesn't. Okay.
So does it move? The top one is to move ahead like to the next send.
Right. Right. So this is actually maybe a good point to mention another sort of advanced optimization that some people have used. So a lot of codes we see have MPI barrier calls in them. Right? And in fact, there's a wonderful paper that uses theorem-proving approaches to discover FIBs, functionally irrelevant barriers. And so these are barriers that somebody put in the code, but they don't do anything semantically, and they eat time because they're a barrier. So you can think, well, I should remove all of those FIBs. Except, say I change my abstract machine model just a little bit, and I say that I've got exactly the same behavior, but I have a really fast barrier. And so I've got hardware that allows me to do an MPI barrier call, and it only takes, it can't be a few cycles because of speed of light limits. But it's about as fast as I can get. So it's some small multiple of the speed of light propagation time across the machine. Well, if I went back to this code, and I put a fast barrier here, a really fast barrier here, what that does is keep processes from running ahead. If they don't run ahead, I don't get this contention at the destination. So I can speed this code up by adding barriers to it, but only if the barriers are blindingly fast. Because in that case, what the barrier is doing is preventing you from contending for some other resource that slows you down. Right? So, and one of the reasons I mention this is that some systems, like Blue Jeans, have blindingly fast barriers. And so you may find some code that has been optimized for communication time that uses barriers. You might think that that's silly. It's not performance portable because in many cases the barriers won't be that fast. And in some cases, only barriers over certain collections, certain communicators will be fast. But in cases where you've got that, you can improve the performance of this. There are other things that you can do to add communication to improve the performance by controlling when communication happens to try to avoid contention, essentially avoiding communication that effectively blocks, but is constrained or slowed down because it's using some shared resource. So again, one of the messages you got yesterday, particularly during Pete's dinner talk, is it's not just reducing the number of operations. It's reducing the amount of communication does not necessarily slow down or speed up your code. It may slow it down. Right? And so understanding how that happens is the reason that I wanted to show you this example so that you can start reasoning about where those performance problems come from. Okay, okay. So as I said, that ordering of sends, that's one of the culprits. And you impose a particular, not quite delivery order, but sending order that you didn't really need. You just did it because it was convenient in your code. But the system has to obey that. And so that slowed things down. It means bandwidth is being wasted because you've got places where you're trying to send data, but the receiver can't absorb it fast enough. And so the senders are told to slow down. That's what usually happens. And this also happens, for example, if you're using memcopy and shared memory. And in this case, this is a problem because memcopy is also blocking. So if you do this sort of code using a shared memory or one-sided model where you eliminate the receives because it's one-sided, but use the sends as memcopies, the sends are blocking. And in that case, you're just not going to be able to get good performance. What you need in that case is what is effectively a non-blocking memcopy, which some PGAS models have added because otherwise you get this sort of problem. Okay, so the fix is to just break down and use a non-blocking send instead of the blocking sends. What you've done by making use of that non-blocking send is say, here's the data that I want delivered, but I don't care in what order it's delivered. And if the MPI implementation is good enough, what happens is that as it's trying to deliver data to, say, this process, it also knows that it's trying to deliver data to the surrounding processes. And so it'll try to fill those pipes or fill those messages up and keep everything busy. And what you end up having is effectively four steps where data is moving in all directions until you're done. And if you look at this, well, now everything's non-blocking, so you only see the times in the wait-alls. These are the two interior processes. These are the ones with 4 neighbors. These are the processes with 3, and then there's a couple with 2. Gives us about the time that we expect. And the group that had their code, when they made this change, then they got the performance that they expected and that they knew what it is that they were doing. Okay. So the thing to really remember here is that when you do send receive or you do any sort of delivery of data from one place to another, it has these 2 components. And we tend to think about the data transfer as the big component. And that may be where a lot of the work is, particularly if it's a fair amount of data. But many ways, the synchronization, the understanding when the data that you're sending has been sent so that you can reuse that data area, that array, and understanding when the data has arrived, when the receive is completed so that you can use the data, that is, in fact, what is the most complicated part internally and the most important for performance. Lots of codes that we see tend to have more synchronization than is required. These codes that do this bulk synchronous programming, the BSP that Pete mentioned, BSP is very convenient. It's very easy to reason about. In fact, the BSP model includes a performance model for an abstract machine as part of the programming model design, which is really wonderful. But it has all of these synchronization points. So synchronization points help you reason about the behavior of the code, but they also impact the performance. So what you should be doing in many cases is, particularly if you're moving non-trivial amounts of data, is use the non-blocking routines and wait all and allow the MPI implementation to decide how to order the delivery of the data. Okay. Any questions about that? Yeah.
Since there is a regular send and regular receive for that, are there dangers to using? Why would you ever use the regular one? Is there dangers to use the Isend and Irecv and whatever?
So the dangers in using the non-blocking ones, there are two dangers. One is the danger that was pointed out in this computer scientist review of MPI is that you've said, here's some data, here's like for the send, here's an array. The programmer has to promise not to modify any part of that array until that send completes, until the wait all. So, and that might be separated by a lot of code. There's a lot of danger that they might forget, and then there'll be a hard to find bug. Right. So that's a real issue. But it's if you're very disciplined, then you're okay. But from a point of view of the programming model, it is a sort of hazard that your code slowly gets bigger, you forget, you misuse it or something. In fact, do you know about futures? How many people have heard of futures? Okay. So in programming model or programming language design, there is a cleaner way to handle this, which is called a future. It's basically, here's something I want you to do in the future. Now the compiler will know about that. And for example, if you said, here, move this data in the future, and then you touch the data, the compiler could give you a compile time error message. But because MPI is a library, and it has to be a library because we knew we couldn't convince the compiler people to add what we needed to it, we have to have this sort of compromise. Okay, so it's just a programming elegance, programming maintenance issue. But it can be real as codes get bigger. The other thing is that there is overhead, there's performance cost to having these non-blocking operations. So the nice thing about, for example, blocking send is I've got the data, I know what I want to do with it, I can write my code to just push it out until it's done. All it has to do is keep talking to the hardware that moves the data. And so you can time this particularly if you're moving very small amounts of data, using a send is going to be the fastest. Okay. And the same sort of things are true for the Irecvs. In addition, for Fortran users, how many of you are Fortran users? Good, okay, I feel vindicated. I have Fortran version, we're gonna show C versions of the code, but there are Fortran versions of the code for you to look at. There are nice things about Fortran. So the reason why I mentioned Fortran here is that Fortran was designed for lots of performance optimizations, and a good compiler will take aggressive and ruthless advantage of those. And Fortran doesn't know anything about non-blocking operations. It doesn't know about it for non-blocking I/O, doesn't know about it for message passing. In fact, the most modern Fortran has had things added to it to help support MPI. There's a very nice collaboration between the standards committees. I do want to say that the stuff that we needed in MPI really isn't specific to MPI. It would be true for anything that was going to move some data somewhere. So if you wanted to write a non-blocking I/O library that wrote to non-volatile memory or to disk, you would need exactly the same things that we put into it. Okay. So the issue is for non-blocking routines, the arguments that you provide to that non-blocking routine, the Fortran compiler itself might decide, oh, you've called that routine, you're done with it. And so with very aggressive optimization, you can sometimes get problems that are incredibly difficult to find because the compiler has, for example, optimized away some array that you had allocated. Now, again, with the very newest Fortran specification in MPI and the MPI _F08 module, and compilers that implement Fortran 2008 plus a special extension, you can tell the Fortran compiler just about enough stuff so that all these things become really safe. Short of that, you have to be careful. One thing you can do is not compile the pieces of code that do the MPI communication with the highest levels of optimization, because that's where the compiler might mess things up. There are also some things you can do to trick the compiler into thinking that you're still using the data. And if you look at either the MPI 2 spec or the MPI 3 spec, there's a whole section on dealing with those sorts of Fortran optimizations. And why isn't it there for C? C doesn't need it because C, because of anonymous pointers, the C compiler can't do the things that a Fortran compiler does for performance. So the reason that you might be reluctant Fortran programmers, the reason your advisors are still making you use Fortran is that Fortran can be faster. Okay, so and that's another hazard, potential hazard for using the non-blocking calls. Having said that, for these reasons, it's still worth it. You just need to be a little careful. Okay. Any other questions? Yes?
If we order the message, for example, by numbering the processors, the even number processors could send to the odd numbered processors. So will this method have a bandwidth contention problem you mentioned?
So, okay, so the question is, could I say have like two phases, you know, odds send to evens, then evens send to odds, or so forth, in order to avoid the contention? So yes and no. For these sorts of regular arrangements, I can work out phases. And in fact, I will show examples in the afternoon where we did exactly that. There are two reasons why this is hard to do in practice. The first is that doing that match of odds to evens is very hard to do if you don't have a regular pattern of communication. You know, making sure that you've got the exact matches. So in the theoretical computer science, and again, one of the critiques of the original MPI is that you never, in fact, need non-blocking communication because there's always some sort of way to order the sends and receives so that they can always be done with blocking sends and receives and get the correct result. Right? And so from that sort of theoretical standpoint, you don't need them. In practice, it can be incredibly difficult to figure out that schedule. Plus, you've got this performance issue that ordering may or may not address. That's the first one. The second and much more difficult issue is doing that odd-even ordering only works if my sort of virtual network, my abstract model of the network, matches the physical network. Right? And that's the hard one, because there is no standard portable way to even find out what my physical network looks like. Right? MPI is all in terms of these MPI ranks. There's a virtual topology, which is virtual mapping of processes onto some abstract hardware model. But to avoid contention, I have to deal with the real world. I have to deal with the physical mapping of the processes to the hardware. And so that it also makes it more difficult. So by using just the non-blocking operations, I allow the system to take care of that. And again, sort of reflecting what Pete talked about last night, I'm taking advantage of the MPI runtime to deal with complexities in the physical hardware that I either don't want to or don't have the tools to attack. Okay, all good questions. Any others? Yes?
So I was wondering if you had thoughts on just the master worker problem in general, and as far as synchronization goes. So, you know, say you have 100 jobs to do, and you have a a master that's distributing it to 10 workers and you want to keep the workers busy all the time. So I guess the two ways I've seen that done is with MPI wait any, which seems like the best way to go based on what you've discussed here, or a cruder way would just be to keep cycling through all the workers, and checking for one ones that work. So what are your thoughts on the best way to deal with that?
So there are some libraries for this. So my first recommendation is let someone else write the code. But now to answer your question, and in fact, Rusty will, I think, talk about somebody else writing the code. But to answer your question, I actually think that wait any is almost the right answer. The true right answer is wait some. Okay, so this example used wait all. Let me maybe go back. So this one just does what it says. It waits until all of the requests are satisfied. Wait any waits until one is satisfied and then tells you which one it is. Well, if you're doing this sort of master worker, what you usually do is once you've got one, you repost because you might get more from that same person. But wait any is not guaranteed to be fair. So what might happen is if someone is sending bunches of stuff to that master, the master might just respond to the same source over and over again. What wait some does is give you everyone who's ready. And so that's what it's supposed to do. And that's what most implementations do. And so it's the standard doesn't guarantee that it's fair, but sort of by definition, it means that your code is going to handle all the processes that are ready. You can repost them all and do it again. So that's why I would use that, unless you're absolutely certain that because of the structure of the computation, you're unlikely to get into this sort of mode where you might end up servicing the same process over and over again. Right? So that's, again, one of the places where people will see scalability problems. So like you write the small code, you do that, you're likely to receive from everybody. But as you start having larger and larger collections of processes, there's a risk that you'll starve some of them. You'll just not get to them because other people are sending you data that, again, trips the wait any. Yes?
You have covered mostly the bandwidth bound cases. Can you talk a bit about the latency bound cases and whether you think it is, well, how do the two types of implementations compare, the blocking and non-blocking, and whether the non-blocking can be as fast as the blocking at all, or?
So thank you for asking that. So what I've talked about here really is the bandwidth bound side. So I was sending edges or faces of data. There's a fair amount of data being moved. If I'm just moving small amounts of data, a couple of words, the non-blocking routines in all of the implementations of which I'm aware add a fair amount of extra overhead. So one of the things that you can do in what is not formally a correct code, but in practice will work, is you can just use sends for data that is small enough. Right? Now, again, an MPI implementation isn't required to do any buffering at all. There was an implementation by one of the major vendors probably 15 years ago now where that buffering size was 0. But today, most implementations will send a few words of data. And the reason for that is that the way data is sent, if you do either a send or an ISend, in both cases, some data is sent with a send. That data is a description of the data. So it's how long the message is, what the message tag is, what the communicator is, maybe what the rank in the communicator of the source is. That's a certain wad of data, sometimes called the envelope. Now, most modern networks don't send variable sized bits of data. They send a thing maybe called a FLIT, some sort of packet. So after I filled part of this packet with some of this data, this envelope data, there's some left over. And so most implementations will send at least that much leftover data with an MPI send. And in order to deal with the latency bound side, rather than just ignoring the rest of that packet and putting the data in the next packet, you always put a little bit in the first packet. These are sometimes called short messages as opposed to eager, which is envelope followed by some packets of data. And so in most cases, at least that much data, whatever's left in the packet, will get sent. And so for those, there's no reason to do a non-blocking send because you'll still send that whole packet. And in the non-blocking case, you then also have to populate a request and return it, which then has to be given to wait, which is going to have to check to see if it's completed. This is a lot of extra overhead. So in the cases where you're sending small amounts of data, you can often use just sends. But note that if you're organizing the code as sends followed by receives, there is a risk that you'll block on those sends. Okay, so I'm just, you're really trying to squeeze scalability out of something at the latency end. You have to deal with that part. Does that answer your question? Okay.
And what is the, just an addition, what is the what about the intermediate regime? So assuming kilobytes of data where you may not it just doesn't fit in the envelope.
Well, we'll see some data this afternoon. One of the things that you can do on some systems is change what's called the eager limit. So you may be able to say, I want the system to eagerly send, even if it means buffering data that's up to a certain size. And there'll be some limit of that, a point beyond which the system will be unwilling to go. And it has its own scalability problems because the easy way to implement the code is to set it up a buffer space of a certain size for every possible process that might send me data, which would be the size of CommWorld. A more sophisticated implementation can allocate that buffer space only for processes that are in fact sending me information. And in a scalable computation, by definition of scalable, that will only be a small number, depending on how strict a definition of scalable you want. It'll either be a constant number of processes or something that's little o of log p. So in that case, you could handle more buffer space reserved to the processes with which you're communicating. But that's a trade-off there. If I have to effectively do another indirection to find the buffer in that case. Right? So it's all trade-offs. Other questions? Yeah.
Related to small data, in the case where you have to send the data including the corner points.
Yes.
In the case of 3D, it is like the same small data is sent to 7 other neighbors. So what would be an optimal way of doing it?
So there are two ways to do that, and you'll see one way. I'll do just for 2D in the example codes we'll be working with today, which is called the diagonal trick, and I will show that in a little while. And that allows you to avoid the single word sends at the cost of additional synchronization. You could think about using a blend of code to do this. So you could use the blocking sends to send the corner points. This is probably the fastest way to do it. Then use the non-blocking certainly for the faces, possibly for the edges. If you don't use them for the edges, you'll run a risk of deadlock, but you could give that a try. then I'm trying to think about the order. You probably want to do is then do the receives at the very end, the short receives at the very end, because then the danger that you will be waiting for something to arrive that's late will be the lowest. Now, I've said that. You shouldn't do that unless you've got some reason to believe that the cost of those small sends and receives is impacting your scalability. So you should not do that speculatively. You should have some way to understand both the impact of the overall communication on the scalability of your code and the impact of the particular cost of those operations. So the extra overhead may be on the order of a microsecond. Okay, yes, a microsecond is a long time. But if you're sending enough data that you're spending 30, 40 microseconds total, maybe it's not worth it. Okay. So again, that's the having an expectation and understanding of the total time that you're spending is really important here. And there are other things that might interfere more with the performance. Okay. Other questions? Okay. So now what we're going to do is look at sample code that we have for you to play with today. And we picked this one because it has all of the sorts of features of a simulation code, but doesn't involve a differential equation. Okay, so we use a thing called Conway's Game of Life. How many of you know about Conway's Game of Life? Okay, this is good. So this is a really fun thing. It's really a cellular automaton. It dates back to 1970. It was described in the mathematical games section, Martin Gardner's column in Scientific American. It has all sorts of interesting behaviors. And I'll show some examples, but there were many interesting questions. So for example, you start with a population and you let it evolve or let it grow and die. And so one question is the population bounded? Right? You might, right? So if you've got something and this life goes on, can it grow without end? And it turns out that it can through a pretty wonderful pattern that somebody discovered called a glider gun, which creates little pods of life that fly off into infinity. There are a bunch of other interesting things that you can do with it too. The way it works is this. You've got your regular mesh. We've got a cell. In each iteration, we look at each cell. We look at the surrounding 8 neighbors. And in the next iteration, that cell is still alive if a few rules are followed. So if there are exactly 3 neighbors, the cell is alive. Or if the cell was alive in that iteration and there are 2 neighbors, the cell is alive. Right? So we can get a birth by having an empty cell with 3 neighbors. A cell lives as long as it's not too lonely. If it's overcrowded, they die. It turns out that you get some very interesting behaviors in this game. In this case, that initial pattern ended up completely dying off. There are other patterns that are stable. And we'll see some of those. Stable in the sense that you reach that point and they never change. So the most common thing that happens in sort of a random pattern with this is either everybody dies off, you get extinction. You might get a collection of stable figures. So for example, a box, if I have no life, and I've got these 4 filled, each one of them has 3 neighbors. And so by this rule, it lives from iteration to iteration. So if I do that, then it just stays here forever. And then there are oscillators that follow a sequence of moves and then repeat. So it's really cool. So how do we implement this? So part of this is, how do you think about making a piece of parallel code for one of these simulations? And often the right way to do this is to begin without thinking about parallelism, and then figure out how you want to divide the problem up. So we want to implement this. We set up a 2D matrix to hold the state. We'll actually do 2 matrices. So there's the current iteration and the next iteration. We'll initialize the matrix including boundaries. So the real game of life is on an infinite board. We're going to do one on a finite board. You can, of course, do implementations that are effectively infinite boards, but that makes the code more complicated. And the example code that we have is just going to generate sort of a random initial state. So some random number generator drops in life. And each time step, we calculate the new cell state based on that rule. We swap the old and new matrices and continue. So that's pretty easy. So designing the parallel version, we start by thinking about this global array. So some says there's sort of 2 ways to put together a parallel program like this. One is you can start with the non-parallel version and divide it up. And then the other one is you can start by taking a bunch of pieces and try to glue them together. For things like this, I find that it's often easier to start with the serial, the non-parallel version, and cut it up. Okay, so we're going to define the decomposition in terms of this global array and the communication, and then we're going to have the local arrays, which are going to be the pieces that are held on each process. So we've got this global data structure. These are all the mesh points. There's my stencil. In fact, for this, of course, I need all 3 of these. So I need not the plus stencil, but the star stencil. If I was doing a PDE simulation, I would have exactly the same sort of behavior, whether I write it as finite differences or as some matrix vector multiplication. This is effectively the data that's needed for the non-zero elements in the row of a matrix. So I'm doing a sparse matrix vector multiplication. I still have something that sort of looks like this. Okay? So now what I'm going to do is cut it into 9 pieces. I'm going to give each process a piece. Okay, let's see. So now it sort of looks like this. So I've taken my global array and cut it up into these pieces. There might be my stencil. The stencil here, I need this data, which is this guy up here. So I'm going to have to get access to that. Okay, so what we typically do is add halo cells. So we make our local array just a little bit bigger so that we can have a copy of the neighboring data. And so now, having copies is a common thing in the machine. After all, this is what cache memory is for. But in this case, you, the programmer, are going to have to manage this cache. It's not going to happen automatically. This is exactly the place where people find the good and bad parts of MPI. The bad part is you have to do this yourself. The good part is you can do it yourself. And there was a question last night about, shouldn't the compiler do this? Yes, and someday, maybe that will happen. Today, that still remains a very, very difficult problem. So in some special cases, compilers are able to figure this out and do it reasonably well. But once you get away from those special cases, you tend to fall back into problems where our current compilation technology just isn't quite good enough. Okay, so now I've got this data, or I've got places for the data. So this here is going to be a copy of these cells. Now, I should sort of move this around. So I've got a little stencil. What are the transfers? Okay, so remember, this interior piece is the part of the global grid that I own. Right? And I've added these edges around it. So what I can do is I can send my edges to the neighbors in the copy locations. Now I'm going to address the diagonal one. So say in this case I've got a star stencil instead of just the 5-point stencil. So I'm going to need this data here. Well, what I'm going to do now is instead of sending just the points that I owned here, I'm going to send data that I got from my neighbors. And so this piece of data first went over here and then went up here. Now, in order for me to do that, I can't do this send until this receive is completed. But if I do that, then I don't need this single word send this way. Whether that's better or not depends a lot on your hardware. And again, these are all trade-offs. Someone also mentioned last night the dream of performance portability. This is a dream. It's a good dream. One should have goals to aspire to. We're so far away from that as Pete put it, we don't have to worry about our jobs. Okay. So this gives you a way to provide the data. So at the end of this, each process can have all of the data that it needs from the 8 surrounding processes. And now it can just run over all the data for which it's responsible and get the information. Okay. So what does it look like? So here is a piece of the code, and we're going to use G to refer to the global grid. So GJ is the J index for the beginning of my patch in the global grid. We're going to use L for stuff that describes the local piece. So L in J is the number of columns for my patch, not counting the halo. And global J is the global index of the first column of the data that I own, not including the halo, because that's not data I own. And this last one is the starting column plus the number of columns, minus 1 to get to the last one. And the same for I. When people talk about the productivity of MPI and needing something better, the issue that they're talking about is the fact that MPI doesn't provide anything, and there's a little asterisk on that because there's a little bit, but it's really not very useful. It doesn't provide you with anything to help manage these distributed data structures. It gives you everything you need to implement the operations on these distributed data structures, but it doesn't have anything to help you manage the distributed data structures. That's not a problem with MPI, it's just something that it doesn't do. But that's, in fact, the hard thing. And it's so hard that while there's been a lot of work to try to come up with systems that do that, there hasn't been one that has been general, and that maybe there will never be one that's completely general. In fact, some of the more successful work recently, both in HPC and in the general commercial community, has been addressing that problem by dropping the requirement for generality. And no longer claiming that we can solve all problems. We say, if your problem looks like this, I've got an answer for you, rather than trying to come up with a general purpose tool. The nice thing about MPI is the communication is completely general purpose. So whatever you come up with, you can implement here. That's the good part. The bad part is you have to do everything yourself. So why do I say that? As you're trying to manage these distributed data structures, you need to have very organized and consistent ways of labeling them and talking about them, because no one else is going to help you with it. And so that's why I spent an entire slide on what might look really, really obvious. I've done this because you can imagine the sorts of codes we've seen. Okay, so as I mentioned, there are both C and Fortran versions of this code. I'll talk a little bit about this C version. The Fortran version pretty much looks like the C version, but with a couple of small differences that I'll talk about in the right places. So there's the main program is in this file. So there's mlife2d.c or .f90. It runs life with a number of different choices of Halo Exchange implementation and with some different communicators. It runs them twice. Why does it run them twice? Well, the first time you run something, the system might do all sorts of stuff. So for example, it might go get the code. And if you're timing these operations, if you write your code, you do MPI init, you do t equals MPI w time, and you do a send, what you might be timing is the amount of time it takes the MPI, the operating system, to go to the disk to get the code for MPI send. So the easiest thing to do is to run the operations and just throw away the time. Well, another thing that might happen is maybe you've got the code for send, but you haven't initialized the communication. So there's a lot of reasons why the first time through you might get more time. So this code runs them twice is the simple way of doing this, and then prints the time taken for each of those exchanges. moptions.c contains a simple routine to parse the command line options. It doesn't use standard sort of system tools for doing the options. It does use an MPI data type to distribute the options from process 0. So it only assumes that process 0 gets the command line options. Most systems today deliver all of the options to all the processes, but there is nothing in the MPI standard that requires that. And rather than live on the edge, it takes process 0 and then sends it. There's a mlife options struct, or for Fortran, there's a type for this. And you can modify that one to your heart's content. For example, to set up some things to change it. You'll find if you look at the Fortran code that there are, in fact, are a couple of additional options here. I added those while I was testing and thought they'd be good to leave in. File patch.c or patch.f90 contains the routines that map the processes onto a 2D array, sort of a virtual set of processes, and determines the coordinates and sizes of each of the local patches as part of that global array. And again, there's a struct or a Fortran type that contains that information. The file mtiming.c does the timing. So it contains routines to execute the game of life and to time the communication costs. It calls a routine, MPI life next state, for each point. So yes, this is not something you ever want to do because you add function call overhead at each individual point. Some people will tell me, oh, but the compiler can inline that. Yes, the compiler could inline that. Whether the compiler inlines that is another thing that I would not like to depend on. So this is not a high-performance implementation. If Fortran users looking at the C code, you may see weird things like this. This is just a way to call a function through a function pointer. In each of these cases, the functions that are needed for communication are passed to the routine. So it's 5 types of communication. So each of those communications has an initialization routine, a routine to do the exchange, and a routine to clean up. And those are invoked in the appropriate place. In C, we just swap the pointers to the arrays. So that makes it really easy to write the code. So the next state is always an array M2 computed from M1, but the pointers are swapped. Now, I could do that in recent Fortran, but I elected not to do that. Instead, I unrolled the loop by 2. And so the first part does from, I think, M1 into M2, and then the second part does M2 to M1. The reason I did that is that some Fortran compilers, most notably the XLF compiler on the Blue Jeans, when it sees data in Fortran that has a pointer attribute, it decides that under no circumstances whatsoever will it ever vectorize the operations. So for this code, it doesn't really matter. But if you were to change this code to do, say, the heat equation and inline the appropriate operations, you would get really awful performance. Instead, I use allocatable. So for your C types, there's this that Fortran splits pointer data into sort of 2 classes. This case uses allocatable, but then I can't swap I don't have pointers to swap. So I just do M1 to M2, then M2 back into M1. Okay, are the Fortran people clear on that? You'll see the code. Anybody have any questions? Okay. But anyway, I did that because I needed to use allocatable as an example for when you want to get performance out of the code. It's actually one thing in a large project I'm leading. We've been, it was a nasty discovery that we got, that using a Fortran pointers disables the compiler's optimizations. Okay. Then there's a separate file for each of the communication approaches. So there's one that does Isend and Irecv that uses the vector data type. Rajiv will talk about data types after the break. There's a version that does user packing and unpacking, so it always sends contiguous data. But in that mesh, depending on whether it's C or Fortran order, either the rows or columns will not be contiguous data. So so these two do essentially the same thing, except uses MPI to gather and scatter the data. The user does it manually. This uses send instead of Isend. This one, and these all use that trick to do the corners. This one does not. This one sends the corners with an Irecv, or an Isend. And again, well, it wouldn't necessarily be a valid MPI program because it would rely on single word buffering. You could send the corners with MPI send in almost all cases. And then there's also a version that uses the one-sided. The Fortran version has a bug in it, which I have just fixed but not uploaded. Okay. Well, I will upload it before we talk about the one-sided. Okay. And then each of those files, there's an init, it creates any sort of persistent data. The C version can return a pointer to this data. There's an end that frees any allocated object, and the exchange that does the communication for that halo. And then just about finally, there is a routine that does a character or any output, so you can see the life evolve in time. It's a little limited in size. It just uses ASCII terminal commands sequences, so you can use it in the next term. It has an init, a checkpoint, a finalize, and a couple other functions to go along with, like discovering whether or not you can read as well as write. It also provides a sort of general interface to the input-output, so it's an example of organizing the code, so it would be easy to replace this, for example, with calls that dump the data directly into a file, say in binary form. Okay, so what we'd like, well, I'll show the first exercise, but basically what you can do, there's the tarball that has this data, there's a configure. You can go into the appropriate directory, either the C or the Fortran directory. You can do a make. If you're doing this with MPI-CH or Open MPI, you can run it, for example, like this. If you do, this would be 1,000 by 1,000 mesh. In that case, you will not get any display. In fact, to get a display, you have to do a -C, but this might give you a reasonable size in terms of the timing data that comes out, assuming you've got enough cores. This says do 10 iterations and give me the sort of character output. Okay, so now what we'd like you to do, if you haven't already, is try running it. So build it, run it with something large enough, and try making some modification, which I recommend that you test on your laptop first. So for example, I can find out how many people know about persistent communication? Okay. Ready sends. Okay, and send receive. Okay. So let me just say quickly what those are, in case you wanted to go look at those. So I mentioned the overhead of, in fact, one of the hazards you asked about, the hazards of using the non-blocking routines is the extra overhead of setting up this request. There's a way to avoid that, which is a persistent send. And there's persistent receives as well. What those do is allow you to create a request but not initiate it. And so you create that request sort of outside your loop. And whenever you want that communication to start, there's an MPI start and also an MPI start all for multiple requests. And it's persistent in the sense that after you've waited on those requests and they have completed, you can start them again. And so the overhead of creating the request and creating the internal data structures that the implementation needs to handle the non-blocking communication can be done once and amortized over the cost of all your iterations. And so that can help reduce the cost of using these non-blocking routines, particularly for smaller amounts of data. Ready sends is a special kind of send. We also talked about the sort of eager and short mode where I just send the data to the destination process where it has to deal with it. And in some cases, well, in these cases where you just do a send and the data is sent eagerly, that means that there has to be a buffer space on the target process. And so the receiver has to deal with that. What a ready send is this is a really dangerous operation because the code has to be just right. Ready send means that the sending process knows for certain, without fail, that the matching receive has already been posted. Not that it's likely to have been posted, or if things are running at the same speed, it's been posted, but that under no circumstances will it not have been posted. In that case, no matter how big the message is, the sending process can just send it because it knows that when it arrives at the destination, there will be a place to put it. you can't always use these, but in some cases, the structure of the algorithm allows you, for example, to post an iReceive before you do, say, an all reduce. Now you know for absolute certain that when the all reduce exits, all those iReceives have been posted. Any send that follows the all reduce could be a ready send. Right? So if you're doing an iteration in which at every iteration you're doing some convergence check, then you might be able to do this. And again, that can lower some of the overhead that you see. And in the middle range, this can be important. And this afternoon, I'll show some data that will allow us to talk a little bit about where that middle range might be. And then send receive is a way for two processes to send and receive data from each other, again, without using a non-blocking operation. In fact, the send receive is more general than that. It allows you to send to anywhere and receive from anywhere. You still have to organize, it is a blocking operation, so things would have to be ordered properly. But you can imagine doing a sequence for this regular grid where you do shift left, shift right, shift up, shift down, all done with send receives.